Welcome and thank you for downloading the SteerDuff podcast.
Second lecture of Aerodynamics. I got two questions in the break that might be relevant for others. Apparently problem 4.4 gave some problems. It was in the wrong unit, sorry, the feet and the pounds. But I mean, doing calculations shouldn't matter on the dimensions, but on the exam and for your further career, SI units are core. I will give everybody the chance because 4.4 is sort of crucial to practice. Practice it. Next lecture I will start with discussing problem 4.4. Then question number 2 I got is how to actually practice aerodynamics and learn for the exam. Because of course what I tell here is in much less detail than in the book. Because if I would read out the book, we would spend, I think, the whole year on aerodynamics. I would like it, but maybe it's not optimal for you. The true thing you need to do, so I don't mind if you read the book or don't read the book. The book is a nice, it has the core bits in it, but it has stories around it, or it explains it a few times. So you can read that as sort of background information. The derivations and the formulas, the equations are really core, so you should know them by heart. We don't have formula sheets. And you should be able to work with them, because aerospace engineers actually design aircraft, compute stuff. So what you should do is not only know the equation, but should be able to manipulate with it and determine important things, speeds, lift, drag, so really manipulate with them. So it depends on your learning style, what is optimal for you. Personally, I always I advise to practice a lot. So really try problems, old exams on Blackboard, the problems I give you as homework, the instructions. That is really core. If you can do that and really do that successfully, you can still read the book, but it's not crucial. If you don't understand what you're doing, well, look at the Collegiorama, the book, the lecture notes. But it depends on your style. What we ask from you in the exam is really solving problems. So solving typical problems. The problems I do here at the board, in the lectures, the problems that are in the book, and the instructions. Yeah? Any questions about that? Okay, then we continue with our lecture. Summarizing, so the one slide, I talked for 2 times 45 minutes, but this is really the core. Of course, the equation of state, P is rho RT. I talked about the fundamental quantities, and then I talked about incompressible flows and the basic relations, the continuity equation, conservation of mass, and conservation of momentum, which for incompressible flows comes down to the Bernoulli equation. So these two, continuity equation and Bernoulli's equation, crucial. Please don't forget the Euler equation, which was the more general relation for momentum conservation in differential form. We will use that later today again. And please be aware of the limitations, of course. We needed to make a few assumptions to be able to derive this. Steady flow, we neglected friction, and we neglected gravity in the derivation of Bernoulli, right? And of course, incompressible flow, because otherwise we would have the rho on both sides of the continuity equation. So rho AV is constant, and then rho 1 A1 V1 is rho 2 A2 V2. Okay, so now today we're going to make the step to compressible flows and see if we can actually derive relations like the Bernoulli equations, relating speeds to these scalar quantities, but then for compressible flows. We have, of course, the Euler equation in differential form, but can we get some more? And sort of a nice picture is the first picture of actually a shock. This is a shock in front of a bullet, which has a supersonic speed. And it is shown with a Schlieren image, which is used to visualize density gradients, changes in your flow. So today we will tackle Anderson chapter 4 still, but then paragraph section 5 till section 9. And core guy in this lecture is Ernst Mach. And he there's a crucial dimensionless number, the Mach number, which I will introduce to you later, maybe you already know it, that's named after him, and that's really relevant for compressible flows. So the picture was taken in 1887, actually. Okay, so today, thermodynamics. Why thermodynamics? That's with work and heat. And these concepts are crucial for compressible flows. I will introduce the topic of isentropic flow, because compressible flows in general we can derive relations for, but then we run into the partial differential equations again, so we need some simplifying assumptions. For isentropic flows, we have simplifying assumptions such that we can derive simple relations like Bernoulli's law for incompressible flow. We will get to the energy equation for compressible flows. A very nice simple relation which you can derive for isentropic flows. So thermodynamics, the first law, specific heat and equations for a perfect gas, isentropic flow, and I'll work my way up to the energy equation. So what are we talking about? Well, we're talking about systems of unit mass, and the first law of thermodynamics says that the internal energy of this system, and we're talking always per unit mass. So the internal energy of this system per unit mass can only change if you do two things to it. Perform work on the outside, on the boundary, so push it in or pull it out, or heat it from the outside. So that's two ways that internal energy of this system can actually change. So heat added, that's the red arrow, or pushing in or out at the boundary. So if you write that into the equation, dE, so on the left side, that's the small change in the internal energy of a system per unit mass. And that is actually equal to heat added or taken away per unit mass, so del Q, plus the work done on the system per unit mass, del W. And that's the first law of thermodynamics. You don't really need this first law as aerospace engineer, but we start from this, actually in two instances, and derive from it equations that we actually work with. So it is a sort of at the core of our compressible flow theory. Now, let's first think about the work done on this surface per unit area. So for this work done, we assume a small area dA, a boundary element of this unit mass. Now, what is it actually that might be pushing it in from scalar flow quantities? It's a force, right? What force do we have in our flow? Pressure. Pressure is a force per unit area. So we have a pressure around this, surrounding it. So in normal direction, we have a P on this small blob. And the work done at the boundary, so this del W, so the small change in work, is due to the pressure. If there's a high pressure outside, a lower pressure inside, it will be pushed, the boundary will be pushed inside, like this. And then the force actually doing this is pressure times area, so P times dA. Now, the work actually performed by this force is force times distance, right? So suppose I'm pushing this in distance s. Then the work performed is force times distance to push this small thing in, so F times ds. The force was P times dA. So we have then, or it's called S in there, so force work is F times S. F is PdA on this small thing. Now how do we get the total work on the whole system? We sum or integrate over the entire boundary of it, right? So all the small area bits we add together. So we integrate over the entire area A the work. So del W, the work change is the integral over A, force times distance. Force is P dA times S. And this is still per unit mass, right? P is constant, so we can take it out of the integral. So we're integrating now S, so that's this distance, times area. So that's actually the volume, right? The volume displaced by the pressure. So this is distance times area, so volume. And what is it? It's the change in volume due to this force. And it's per unit mass, so it's a change in specific volume, right? Because specific volume was volume per kilogram. So this is the change in volume. And it's still per unit mass. So you get something that is a change d meters squared over kilograms, right? So you can write this as P times the specific volume I showed you yesterday. dV, the change in specific volume. And what sign should it have? Is the volume increasing or decreasing due to the higher pressure up here? It's decreasing, so it is a negative sign. So it's minus PdV. So the work done on the entire system per unit mass, you can rewrite to be minus PdV, and this is the curly V, the specific volume. Now we had the first law of thermodynamics stating that dE is dQ plus dW. We can rewrite that as dQ. Here, this one, dQ is equal to dE minus del W. And now I can substitute what I just derived into this equation. So I can get then that the change in heat, the heat performed at the system per unit mass is equal to the change in internal energy per unit mass plus PdV. Now we define something which is called enthalpy. And the enthalpy is defined like this. And that's something you should just remember or know. The enthalpy is internal energy per unit mass plus PV. So E plus PV. Then the differential form, if I differentiate, I get dH is equal to dE plus D of PV, right? And then I do the chain, apply the chain rule. So the differential of PV is PdV plus VdP, and still specific volume. So I also have this relation, and I have this relation. Now I can combine both. So starting with this one, so delta Q is dE plus PdV. Here it is. I can substitute the dH I have here. So I have a relation between dH and dE. So I substitute now, or replace this dE with this equation, right? So I use the fact That's dE is equal to dH minus PdV minus VdP. So it seems a bit boring, but what you get then, so if you replace dE by this, we still have the plus PdV. You see that this one drops out, minus PdV plus PdV. So we can also have a relationship like this between dQ and dH. So two key relations. This one, dQ is dE plus PdV, so pressures and specific volumes or densities. And if I use the enthalpy form instead of the energy, I get dQ is dH minus VdP. Now what I now do is I have either a dP or a dV, so changes in pressure or changes in specific volume. Then what is done in thermodynamics is, say, identifying two processes, either a constant volume process, where I say, okay, I do stuff to my system, but I keep the volume constant, so then dV is 0, or a constant pressure process, say I do stuff to my system, but I keep the pressure constant. And then for these two separate items, I'm going to formulate the equations. So let's start with a constant volume process. Suppose I add heat to my system. I heat it up. I have a system of gas. What will happen if the molecules will move faster, right? Temperature will go up, and maybe also the volume might increase. But what I do here, I say I keep my volume constant. So I have rigid boundaries, heating it up. So changes in volumes not allowed. Just a box, heating gas inside a box. That's process one, a rigid boundary, constant volume, and I can add heat or subtract heat while keeping the volume constant. Then process number type 2 is a constant pressure process. In this case, I say again, I heat or subtract, or add heat or subtract heat to my system, but now I make sure that the pressure of my system internally is kept constant. How do I do that? Sorry?
Frictionless piston?
Frictional system?
Piston.
Yeah, a piston. Yeah. So how do I do that? I change the volume. So having, for example, a piston, 3 walls and a piston, which makes sure it moves such that the pressure is constant. So no pressure changes. Okay. Another definition, you'll probably have had this at high school, the specific heat. And a definition of specific heat is a specific heat constant, and it tells you how temperature changes are related to heat additions or subtractions. And it's defined as C is dQ over dt. So dQ is equal to C dt. So if you add a certain amount dQ with this specific heat constant, you can find how much the temperature will change. And we have then two specific heats, one for constant volume processes and one for constant pressure processes. So CV and CP. Okay, now let's see if we can combine it. So we have two types of the first law of thermodynamics with dQ and dE, the first version, dQ and dH in the second version. And here I have a relation between dQ, this heat, and the temperature. What I'm after is eventually relations for temperature and eventually relating temperatures to speeds. So now see if we can substitute this into these laws of thermodynamics. Now we'll go back to this form of the first law of thermodynamics, right? I just earlier showed you that dQ is equal to dE plus PdV. Now for this one we choose the constant volume process. In case we keep the volume constant, dV is 0, no changes of volume. So then, I don't have any work done at the boundaries, and I just have that changes in my internal energy are directly equal to heat added or subtracted from the system per unit mass. Nee? Okay. So what I then do is realize that this dq that I have here, my heat added or subtracted, I can substitute my specific heat just defined earlier, right? So dq is equal to c dt. We are in a constant volume process, so dq is equal to cv times dt, right? Oh. So dq is equal to cv dt, so that gives me that dE is equal to cv dt. So changes in internal energy per unit mass is equal to the specific heat at constant volume times dt. Now that's easy. Now I can integrate each side, and I find E is equal to CVT. So I have a direct relation between internal energy per unit mass and temperature, and it's linearly related, and the only thing that's in there is the specific heat at constant volume, so CV. Now I play the same game, but with a different relation from the first law, where I didn't have dVs, but I had dPs. And of course I play the game now for constant pressure processes, so my dP is 0. So for constant pressure processes, dP is 0. I start with a different form, relating the enthalpy to the heat added or subtracted, and that was this form, right? dQ is dH minus VdP. Constant pressure, so dP is 0, so direct relation, changes in enthalpy per unit mass is equal to changes in heat. Then we're at a constant pressure process, so I substitute, play the same game as here, the specific heats for this dQ, so then I find that dH is Cp times dt. Direct relation between enthalpy per unit mass and temperature. And I can integrate it, and I find this H is equal to Cpt. And these, interesting enough, I derived them for a constant pressure process and a constant volume process, but these relations hold as long as you have a perfect gas. So so you don't now need anymore these specific processes. You can remember E is Cv times T and H is Cp times T. So temperatures relating to internal energy per unit mass and enthalpy. Okay, so that's something to remember. Of course, interesting is the values of this specific heat constants. For air, at normal temperatures, so below 600 Kelvin, you can work with the following Cv and Cp. Yes? Oh, sorry. Thanks. Yeah. I get a question about that I use the same formula for the specific heats. Well, I used the same formula, but at different processes. So I recognize the constant heat process and the constant volume process. So indeed, it's the same relation, but it's a different C. So it depends on your process, actually, what this specific heat constant is. For constant volume processes, I recognize this CV. So that's dQ dt at a constant volume. So it's not in general true, but it's for a constant volume process. So this CV is different from the CP, which is how your temperature is related to heat added or subtracted at constant pressure. So as you see here for air, they have different values, right? So they are dQ over dt, so how much does your temperature change when you add heat? But they're different for different processes. So if you keep the volume constant, you have 720 joule per kilogram Kelvin. If you keep the pressure constant, you need 1008 joule per kilogram Kelvin. So it depends on your process. Yeah? For air. Okay, and an example with that. So this is example 4.6 from the book. Simple, but just to practice the basics. So please calculate the internal energy and enthalpy per unit mass at standard sea level conditions. What do you need to do? Where do you start? Find the internal energy in the work. Okay, so enthalpy indeed, so E. So what are the relations for enthalpy? Yeah, question here, can you use the Boltzmann constant? Yes, but that gives you the kinetic energy, and this is the internal energy, and that consists of kinetic energy, but also more. So it is, it's sort of a slightly different relation. And so enthalpy, does anyone remember the enthalpy relation? Yes, CPT, and internal energy. So what do we need to start with to find enthalpy and energy per unit mass? Temperature at sea level, which is 288. Thanks. And what is the dimension? So we do find the internal energy, CV times T, CV 720, temperature indeed 288, so we find 2.07 times 10 to the power 5, what? Yes? Yeah. Joule per kilogram. Kelvin? Joule per kilogram. Thanks. Because this is energy per unit mass, right? Dimension of energy, joule. Dimension of mass, kilogram. Why not a Kelvin? One second. Dimension of CP is joule per kilogram Kelvin, but we multiply by Kelvin, right? So the internal energy per unit mass, joule per kilogram. Questions? No? No more questions? Okay. Now we go to isentropic flow. Huh? So what I do now is I define a specific type of flow called isentropic flow. And that is flow where the entropy is constant And that is the case when I have two, for that I have two requirements. Number one, it should be an adiabatic process. What does adiabatic mean? I don't add or subtract heat, so del Q is 0. In addition, so we don't add or subtract heat, we should not lose heat in dissipative effects. So friction in a flow is a way to transmit kinetic energy, so motion energy, into temperature heat. And that is irreversible. It's very hard to get from the heat you lost, again, speed back. So we should have no friction, no dissipative effects. It should be a reversible process. So once I have an adiabatic and reversible flow, I have isentropic flow. And reversible means for flows really that dissipation is not there. Does it make sense for aircraft? Yes, it does. Only inside the boundary layer, very thin layer, typically if you fly fast, close to the object, you have that dissipation plays a role. Everywhere outside, you can assume frictionless flow. It really, dissipation doesn't play a major role. So there we do have isentropic flow, as long as we don't focus on the boundary layer. And isentropic flow, adiabatic and reversible, both. Then we have the case that our entropy is constant. Does that mean that the temperature is constant? No. Temperature can change, of course, with pressures and densities, right? Equation of state. It does not change because I heat it or cool it or because I have friction, yeah? So from point to point I can have different temperatures due to pressures and densities changing. Okay. Now let's play the game again, but now for my isentropic flow. What do I have for my isentropic flow? I don't add or subtract heat. So delta Q is 0 now. So again, I start with my two forms of the first law of thermodynamics, the one with internal energy per unit mass and the one with enthalpy per unit mass. I had the relation dQ is equal to dE plus PdV and dQ is equal to dH minus VdP. For isentropic flow, D is equal to 0 because dQ is 0. I have an adiabatic process. So as a result, this one is 0. So my dE is equal to minus PdV. So here it is. So minus PdV is equal to dE. And I just derived, right, that this internal energy is equal to CV times T. And this C is a constant. So dE is equal to CV times dt. So I now have a relation. Please bear with me because this is quite an interesting relation. I have here pressure, specific volume, so 1 over density. So pressure, density, some constant, and temperature. And what do I have here on this side? I have VdP is equal to dH. So VdP is equal to dH. And dH I just derived is equal to Cp times dt. So again, a relation between specific volume, 1 over density, pressures, and temperature. Yeah? I'm going to use this in more instances, but the first thing you can do from this is derive now, because the problem I have here, I have pressures, densities, temperatures. 3 unknowns, 2 equations. If I manipulate them in such a way that I can eliminate one and end up with 2 unknowns, it's more interesting because I already had the equation of state. P is rho RT, so pressures, densities, and temperatures. What I'm looking now for is a relation between, say, temperatures and densities, for example. Now, how do I do that? Ta-da, I divide them. Ta-da. Why? Well, they both have in the right-hand side dt, right? CV dt, Cp dt. So if I divide this equation by this equation, or I divide this equation by this equation, on the left-hand side I have minus PdV divided by VdP, okay? Doesn't look too stimulating, but okay. But on the right-hand side, I have CV dt divided by Cp dt. And look what happens. The temperature drops out, right? Good news. Just pressures and specific volumes and constants. So this is a bit of a mess. So I collect all the pressures on one side, all the specific volumes on the other side. So, and I prefer to have the differentials on top. So dP, this one to that side, over P is equal to minus dV over V multiplied by 1 over this one. So this relation, after sort of some magic on the first law of thermodynamics, isentropic flow, adiabatic process, dq is 0, I end up with this relationship. And it tells you how much pressure changes in relation to density changes. And actually, we only have specific gas constants, a ratio of the specific heats in front. And quite often we use gamma for this ratio, because this ratio comes back in all different forms. So we write it as, it's a bit tedious to write all the time, CV divided by CP, CP divided by CV, so we replace it by gamma. And for air, we have the 1008 over 720, so this value is 1.4. So then I can simplify this a bit. dP over P is equal to minus gamma dV over V. And this gamma is dimensionless, right? And this is actually a dimensionless equation. On the one side, I divide pressure changes by pressure. On the other side, I divide specific volume changes by specific volumes, right? Okay, now what do I do? Integrate, thanks. Yeah, you love it, right? Integration. I studied math, so now it's the fun starts for me. Okay. So what is the primitive value of 1 over P? LMP, thanks. So, LMP between state 1 and state 2. So what do we integrate? We would like to relate pressures and densities, or pressure and specific volumes at one point in the flow, to pressures and specific volumes at the other point in the flow. So we integrate from 1 to 2. So we get LNP. So the primitive value of 1 over P LNP is LNP. And on the right-hand side I have minus gamma still there, times LNV between state 1 and state 2. So I get LNP2 minus LNP1 is equal to minus gamma LNV2 minus LNV1. Reasonable question. Excuse me? Sorry? Do you have to derive this at the exam? Yes. So I'll start again. We stay until 6:30 and we'll do it again. No, you have to derive this, but quite often we give you some hints. So what we do say is, starting from two versions of the first law of thermodynamics, the relation between pressures and densities. So we give some hints. Very nice. It's usually bits. Yeah? This is just a bit of calculus. Okay, so this Ln equation is quite perfectly valid, but maybe not in a perfect form. So what we do is simplify it a bit. So we use relations that you know from high school, hopefully remember, between ln's. Number one, ln A minus ln B is the same as this one, right? Ln A over B. And this one, A times ln B, is the same as ln B to the power A. So number one, if we use this one here, I have ln P2 minus ln P1, so that is the same as ln P2 over P1, right? Here, minus gamma times ln V2 over V1. Then I can take this minus gamma in front and use this relation and say that's the same as V2 over V1 to the power minus gamma. So after all this struggle, I have a very nice relation, namely ln pressure at location 2 over pressure at location 1 is equal to ln specific volume at location 2 divided by specific volume at location 1 to the power minus gamma. What do? I take e to the power each side. So ln drops out, and I end up with a powerful relation if you give me information, densities at a certain point and the pressure at another point, I can give you the pressure in the other. So P2 over P1 is V2 over V1 to the power minus gamma. And it's a bit easier to work with density, so rho's, then we realize that specific volume is 1 over density. So then the minus turns into a gamma, right? So over P1 is equal to rho 1 to the power gamma. Yeah? Please remember this is an isentropic flow relation. So if you add heat or subtract heat, it's not true anymore. But for aircraft, flow around aircraft, this is perfectly usable everywhere outside the boundary layer. Also, friction effects should not be dominant. So this is one form, and we call it of the isentropic flow relation. So relating pressures in 2 points and densities in 2 points. What could we do? Maybe we would also like to know temperatures, right? Can we find temperatures? Yes. Using rho equals P over RT. Perfect. Equation of states. So if I substitute the equation of state for my rho's, so rho 2 is P2 over RT divided by P1 over RT1. So here we go. The left-hand side still the ratio of the pressures. Here we had the rho 2 over rho 1. So that's equal to P2 over RT2, RT1 over P1. The R drops out. I have a temperature ratio and a pressure ratio. And what I do with the pressure ratio, of course, I take it to the other side. So please, I still have gamma. So what I do, I divide both sides by P2 over P1 to the power gamma. So dividing the right-hand side by P2 over P1 to the power gamma, this one drops out. Dividing this side by P2 over P1 to the power gamma, I get not 1, but then the minus gamma here. So the relation between pressure and temperature is this one. P2 over P1, 1 minus gamma is equal to T1 over T2 to the power gamma. I do two things. I like the 2's on top, so I rotate this thing, turn it around. So it's T2 to T1 minus gamma, and then I take everything on this side. So I get another relation for pressure ratio, P2 over P1 is equal to T2 over T1 minus gamma divided by 1 minus gamma. Is that clear? Yeah? And then, indeed, so we have P2 over P1 is equal to T2 over T1 to the power minus gamma over 1 minus gamma, and this is the same as minus gamma 1 gamma minus 1. Yeah? And that one is easy to remember. Yeah? So please remember, what should you remember? Isentropic relations, this bit, and this bit. Do I have a summary? Compressible flows, there you are. Okay, and I think now it's time for a break. Okay, shall we start? No? Okay, I'm glad everybody likes it here so much. Yay! Okay. So what do you need to remember? Isentropic flow relations I just derived. I got lots of questions on this last step. So from here to here. So just in case you were not here to ask me and you don't really understand what is happening, is this you can see as a ratio, pressure ratio, P2 over P1 to the power something. Suppose it's squared, right? Suppose this is 2. What do you do to get to a normal just P2 over P1? You take the square root. Taking a square root is 1, doing it to the power 1 over 2, right? So to the power 1 over. So that's what I actually do here. So I take the equation and equate it to the power 1 divided by 1 minus gamma. So then on this side, I get T2 over T1 to the power minus gamma divided by 1 minus gamma. And then I make this a bit more simple. Here I have minus gamma, and this I can write as minus gamma plus 1, or minus gamma times minus gamma minus 1, right? And then the minus drops out, and I end up with my gamma over gamma minus 1. Yeah? So there we are, there we are. So we're working our way up to interesting, more interesting stuff. First, a small practice with these isentropic flow relations, and then to the energy equation. Example 4.8. Question: airplane flying at standard sea level conditions. Temperature at the point on the wing is 250 Kelvin. What is the pressure in this point? Well, it's not too hard now to come up with which relations we should use. So we have our airplane, free stream conditions, where we have standard sea level conditions. So is T at standard sea level, pressure at standard sea level, and some point on the wing, we have the temperature given. So first step we need to do is make an assumption, right? Assume isentropic flow. Does that make sense? Well, we're not heating or cooling the flow. When an aircraft flies, we can have temperature changes inside the flow, but due to the flow quantities, pressures and densities changing, we don't heat it. We don't have a fire or a cooler. Friction is also, negligible because we don't look inside the boundary layer. So this point is outside the boundary layer. So we can assume isentropic flow. Yes? Oh yeah, turn off the lights. Sorry. On. Higher? Yeah? Okay. We're going to vote. Up, down. We'll compromise. Okay. So assume isentropic flow, then we can use the simple isentropic flow relations. P2 over P1 is equal to T2 over T1 to the power gamma over gamma minus 1. So pressure in point 2, or point A, is equal to pressure in point 1, or infinity, times T2 point A over T infinity to the power gamma over gamma minus 1. What is the pressure at infinity at free stream? 101 10 to the power 5. Why? Standard sea level conditions. The temperature in point A was given, 250. Temperature at free stream, 288. And gamma is equal to 1.4. Thank you. 1.4 minus 1. And then we find that the pressure in this point on the wing, PA, is actually equal to 6.14 10 to the power 4 newtons per meter square. No? Is this funny? Oh, okay. Ah. Okay. Now the last step for today. Nice. We have relations between scalar quantities, right? For isentropic flow, pressures, densities, velocities. But for compressible flows, we have no ideas of the speed. We have Bernoulli for incompressible flow. We have the Euler equation, of course. dP is minus rho vdv. But what do we do for compressible flows? We have the energy equation. And that's what I'm going to derive, make an example with, and then that's it. And the idea, the physical principle is energy can be destroyed, neither created. So we conserve energy. And where do we start for our energy equation? The first law of thermodynamics. Yeah. And we use this form. dQ is dH minus VdP. Still per unit mass, right? Enthalpy per unit mass. V is my specific volume. dP, pressure changes. dQ, heat added or subtracted. Any idea about the next step? Adiabatic flow. Isentropic flow, because the energy equation I'm going to derive today is only easy for the assumption of isentropic flow. So no heat added or subtracted. Adiabatic. dQ is 0. Then I have a direct relation between dH and VdP. So dH minus VdP is 0. This V is specific volume, right? 1 over rho. P is pressure. Any ideas? How do we get, so we have here enthalpy and pressures. Now we would like, of course, to get the speeds in there. What relation did we derive? Generally valid for compressible flows, which has the velocities, the speeds in there. No, Bernoulli is only valid for incompressible flows. So what was before the Bernoulli? Where did we derive the Bernoulli from? Euler, our guy Euler. Euler equation, the differential form. dP is minus rho vdv. So that's relating pressure changes to velocity changes. So it's not too difficult, right? First law of thermodynamics, adiabatic, Euler equations. dP is minus rho vdv. So I have now two equations. One equation with enthalpy and pressure changes, and the other pressure changes and velocity changes. However, my density is still in here. 1 over density, density. So let's see if I can substitute Euler equation into the thermodynamics equation. So let's substitute dP in here. So minus rho, and please note it's a bit confusing with the V's. This is specific volume, 1 over rho. So volume per unit mass, right? Cubic meters per kilograms. This is velocities, capital V. So I put this in here. So minus V times rho times minus. So we have plus V times rho, and then the capital VdV. And please note this V was my specific volume, 1 over rho. So I have 1 over rho times rho, so this one drops out. No, not yet. Half an hour more. So dH is equal to VdV. This helps, right? Now I have enthalpy changes and velocity changes. And I can integrate, right? So I have a differential equation. Yeah. You should be able to do better. I'm here. Okay. No, this was not an invitation. So now we're going to integrate this equation from points to the streamline, 1 to 2. Sorry for the blue, I'll take away the blue for the back rows. What I have is dH plus VdV. I integrated along a streamline from point 1 to point 2. Very simple, primitive value of dH is h, so I get h2 minus h1, right? VdV, similar as Bernoulli, only the rho has disappeared due to the specific volume in there. So I have VdV, primitive value half V squared, half V2 squared, minus half V1 squared. So please see, really quite powerful relation. H2 minus H1, enthalpy per unit mass, plus a half V2 squared minus V1 squared is equal to 0. So I collect all the 2's on one side, all the 1's on the other side. So I find now a relation for compressible flows, relating velocities squared, not to pressures, but to enthalpy. And what can I change the enthalpy into? Temperature. Yeah, internal energy, still a bit hard to work with. Temperatures. So H is CPT. So I have temperatures related to velocities. And this is a key difference between incompressible flows and compressible flows. Incompressible flows, it is small pressure forces driving the speeds, right? P plus a half rho V squared is equal to 0. In compressible flows, we have large density changes and temperature changes driving the speeds. Half V squared plus H is constant. Because if you collect all on one side and all on the other side, I get H2 plus a half V2 squared is H1 plus half V1 squared. So H plus a half V squared is constant. And then H is CPT, so CPT plus a half V squared is constant. What is this constant equal to? Oh, question. I made a... Where did the rho and the specific volume go? Tip, tip. V times rho V is 1 over rho, so 1 over rho times rho is 1. So, easy. No? So what is this constant equal to? So, apparently something is here constant in compressible isentropic flows, CPT plus a half V squared. What would it be? Yes? Yes, total temperature multiplied by Cp, so Cp T0. So if my speed is 0, I have a stagnation point, right, or total point, then I only have the temperature. Temperature times Cp, so I have the enthalpy, so that it's equal to the stagnation enthalpy, right, or the total enthalpy. Yeah? No? Yeah. So, summary of the equations. Incompressible flows, we don't bother about densities, we bother about pressures and speeds. So 2 equations, 2 unknowns. You might need the equation of state to get to rho, but we have V's and P's. Yes, question? Shh, please, please, I cannot even hear the question, please. This equation is valid whenever it's isentropic flows. So it is valid for supersonic flows as well. Problem is, a shock is not an isentropic phenomenon. A shock, I will tell you about that next lecture, I think. A shock is a location, very sharp location with a discontinuous change of pressures, densities, temperatures, a major jump. How does this jump go about? It is dissipative. It's a very dissipative effect on a very small scale. So a shock is not isentropic. But a flow can isentropically expand. So you can have supersonic flow, which is isentropic. But through a shock, you cannot do these relations. But in subsonic or supersonic flows, you can, right? So, yes?
Are they all volumes? Are they all velocities?
Yeah, good news for you. These are all velocities. Because I personally don't like the specific volume too much, so I replaced them all with densities. Well, no. So for compressible flows, we have more unknowns, right? We have density changes and temperature changes that are relevant, so we need more equations. So what is the set of equations for compressible flows? The compressible form of the mass conservation, rho AV is constant. The isentropic relations I derived before the break. Energy equation I just derived. And then the equation of state relating pressures to densities and temperatures. Okay. Then I have one exam question I would like to practice with you. It was from November last year, I think, yeah, 2010. And then, if everybody understands this, no, we can go on, no. Okay, the problem, a supersonic wind tunnel. So good question, can we do this for supersonic flows? Yes, as long as we don't have shocks. As long as we have isentropic expansions, no friction, no heat added or subtracted, that's sort of standard in our tunnels. So then we can apply isentropic flow. So we have a supersonic wind tunnel, air flowing from a very large reservoir, a large pressure vessel, into a throat, so a converging channel. I have a picture on the next slide. To the test section, and in the test section we typically put our objects. We have a few things given. Temperature in the reservoir, 1200 Kelvin. Pressure in the reservoir, 9 atmosphere. So quite high pressure. Actually we have a pressure vessel for our supersonic wind tunnels out there. Temperature in the test section, 310 Kelvin. Mass flow is given, 0.5 kilograms per second. And the specific heat coefficient for air, 1008 joule per kilogram Kelvin. And the ratio of specific heat is 1.4. Number A is calculate the air temperature in the throat using the energy equation. Oh, formulation for speed of sound. Oh, this is wrong. I first need to identify. Oops, sorry. We'll do this later. Speed of sound. Sorry. First, and a few small, sorry, got the other way around. Small section on speed of sound. What is speed of sound? Sound are small perturbations going through air or through whatever medium. And they travel at a certain speed, the speed of sound. And the speed of sound is not constant. It depends on the conditions of your gas or flow. Now the way to look at this, so suppose we have a sound wave here. How does the sound wave go about? It's transmitted through, from molecule to molecule, so through oscillations of molecules. Now before we have the sound wave, we have conditions, pressures, densities, temperatures. After the sound wave passed, we have slightly changed conditions. We can also imagine that we're, instead of sort of sitting here and the sound wave is traveling through the room, we can also imagine that we're the sound wave ourselves, right? We're on top of this thing, and we're traveling through air, and we see then flow coming at us at the speed of sound. And a certain flow flowing from us, which is slightly changed, A plus dA, right? So this is a static observer, and this is an observer moving with the sound wave. Now, what sort of relation can we find for this speed of sound? And it's sometimes called A. In Anderson, he uses A for speed of sound. Quite often it's also C, but yeah, it depends on your notation. But I'll use A. First thing we do is we say mass is conserved. So we apply the continuity equation over a certain area here. So rho AV on this side is equal to rho AV on that side. So rho AV on one side is equal to rho AV on the other side. Now what is the V? The velocity. Suppose I'm here. Then the velocity coming at me is A, and the velocity after me is A plus dA. The density before me is rho, and after me rho plus d rho. And the area is the same. So A is the same, so I have on this side rho times A, density times speed of sound, is equal to rho plus d rho, small change in density, times small change in speed of sound. I can multiply this out. On the right-hand side I get rho times A, rho times dA, A times d rho, and d rho times dA. And these d's are small things. So this is rho A on the left-hand side, right? On the right-hand side I have rho A, so these one I can scratch out. Then I have A times small changes in densities, plus density times small changes in speed of sound, plus small times small, and that's even smaller than this, so I ignore this. This is physics, it's not math. So physicists say, oh, that's small, let's get rid of it. So I have now a relation between speed of sound and densities, right? A d rho plus rho dA is equal to 0, or taking that to the other side and dividing by d rho, I find that A is minus rho dA over d rho. So speed of sound is related to changes of speed of sound themselves and densities. Now what do I do? What I'm going to show you is that speed of sound is related to pressure and density changes, and I use my good old friend the Euler equation in here to get the pressures in. I won't ask this derivation at the exam. dP is minus rho vdv, Euler. Velocity is now speed of sound, A. So I have this Euler relation saying changes in pressure are equal to minus rho A changes in speed of sound. So my speed of sound dA change is equal to minus 1 over rho A dP. I had this already from the mass conservation. And putting them together, I get A is equal to minus rho. And then I substitute dA is minus 1 over rho A dP. Right? So the rho drops out. I have A here. So I find that A is equal to 1 divided by A dP d rho, or A squared is equal to dP over d rho. So my speed of sound squared is related to the pressure changes and the density changes. And I now assume isentropic flow. It's really, a speed of sound is an isentropic process. No friction, no heat comes into play. And then I can say that A is the square root of dP over d rho, isentropic. So that's something you should remember. Now, how do we go about this? So, from the isentropic relations, we have a relation between P and rho, right? Yeah. Which was P2 over P1. So nice. I shouldn't have said it, eh? So if I take a good look at my isentropic flow relations, P2 over P1 is rho 2 over rho 1 to the power gamma. If I now, instead of looking at ratios, I collect everything on state 2 on one side and everything on state 1 on the other side, I see that P2 divided by rho 2 over the power gamma is equal to P1 divided by rho 1 to the power gamma is equal to a constant, C. So, in general, I can say, I'll leave in the middle what this C is. P is equal to P divided by rho over gamma is equal to C. Now I can take the dP over d rho, which I have in my speed of sound. then it's equal to the dd rho of P over rho to the power gamma. So it's D. So here I have P is equal to C, right? So from the isentropic flow relations, I find that P is some constant C times rho to the power gamma. Now I do dP over d rho for isentropic flow. So that is the d rho of C times rho to the power gamma. So that is C gamma rho to the power gamma minus 1. Yeah? I can replace C. I can replace C, right? But yes, question? Sorry. I'm not integrating. Differentiating. I'm differentiating C rho to the power gamma, so that is C x to the power gamma to ddx. So then that is C, this is a constant, gamma comes in front, so it's C gamma x to the power gamma minus 1, right? Then I substitute C from this one. Yeah? So I have P over rho gamma, gamma, rho gamma minus 1. And then I find that this is, so that's gamma P over rho. So the dP d rho for isentropic flow from the isentropic flow relations is gamma P over rho. So A squared, velocity, speed of sound squared, was square root, right? Of dP over d rho. So A squared, isentropic relations. So it's square root gamma P over rho. And that's equal to P is rho RT, right? Equation of state. So I have square root gamma rho RT divided by rho. So the rho drops out. Oh, sorry, yeah, A, thanks. Yeah. So, A, doing all these manipulations, I found a very strong relation. A is square root of gamma RT. Gamma, ratio of constants, R, gas constants, T. So the speed of sound only depends on the temperature. But this means if I significantly change the temperature, my speed of sound changes, right? Yeah. You don't need to know. This step you don't need to arrive. You have to know this. And you have to know this one as well. Yeah? Speed of sound. So we go back to our exam question. Ooh. Speed of sound. Now we know what the speed of sound is. I'll clean up the blackboard while you think about this. Okay. Bear with me for 10 more minutes and you pass your exam. Back to our supersonic wind tunnel. We had a reservoir, large reservoir, and our tunnel, which is a converging tunnel. I have a picture here. The reservoir is sort of before this. Then the air is going through this. We have the throat, which is the smallest cross-section of our tunnel. And then it's diverging again, and we have our test section. And this is going isentropically. So it's isentropically speeding up and speeding up further. So isentropically, flow can go from subsonic speeds to supersonic speeds. Only when it slows down to subsonic speeds again, way behind here, right? If it slows down, that goes with a shock. And then it's not isentropic anymore. Okay, so here's our supersonic wind tunnel. And then in the instruction on the compressible flow, the instruction session, you will actually derive it. But today you have to believe me, inside the throat, the Mach number is equal to 1. So once you have a supersonic wind tunnel, so it has the conditions such that the flow is speeded up to supersonic flows, you will have Mach is equal to 1 at the throat. It sounds a bit mysterious, has to do with really characteristics of your flow physics and the way, the speed with which information travels. Believe me, you'll see in the instruction. Now we need the air temperature in the throat. Using the energy equation, speed of sound, and R. So let's first start writing down the equations, right? So energy equation. Speed of sound with a temperature. And then we have the R is Cp given as Cp minus Cv. We'll also, next lecture I think I will derive this, but now it's given. So air temperature in the throat, we have the energy equation, Cpt plus half V squared is constant. We have A is square root gamma RT. We know that in the throat the Mach number is 1 and we have an R. And just forget about it, or just use the second form of the isentropic flow relations, because that's the second form of isentropic flow relations you get Thursday. So we only know the first form of isentropic flow relations. We can still solve the problem. So, okay, so what do we need to do first? Any ideas? Think. What information do we have?
Well, we can calculate R, and that the speed of sound, so we have the velocity in the throat.
R. Yes. Okay. So the idea is using R and gamma, we're looking for T in the throat, right? So in the throat, typically we write it with a star, T throat, A throat. So if we have gamma and we have R, we can use that one. We can compute T if we know the speed of sound. So we need the speed of sound in the throat, right? Any ideas? Speed of sound in the throat. Mach 1, yeah, so it's equal to the velocity in the throat, good news. So, the velocity in the throat. We made the problem now. If we know the velocity of the throat, we can solve the problem. How do we find the velocity in the throat? We didn't use one thing that was given. Energy equation. Yes. Smart. energy equation. What do we do with the energy equation? We apply it from, at least one side we take at the throat, right? From the reservoir, because there the other stuff is given, right? So from the reservoir to the throat. So that's actually where we start. So the energy equation in the reservoir. So CPT0 plus a half V0 squared is equal to CPT star in the throat plus a half V star squared. So good news, we have the velocity here. We have T0, right? Do we have V0? What's the speed in the reservoir? 0. Thanks. So good. So we have this one, 0, in the reservoir. T0 we know. Do we know T star? Any ideas? Yes? How is that equal to 0? We have a huge reservoir where we start from, and we're taking the flow through a very small channel. So we can approximately say, it's not true for some points in the reservoir, but we can approximately say in this large reservoir, the speed is 0.
So it's a reservoir with air just standing still, and
yes.
it's coming out at Mach 1?
Yes. No. Well, later it's Mach 1, but it's through this. So we have, if we have the reservoir as large as the world, and we have a cross-section like this, I mean, the world will not notice that much. The speed will not change. So it's related, it's in that way. So approximately 0. Yeah? So, okay, so we have, good news, we know T0. Bad news, we have T star and V star in there. Any ideas? Yes. So please, yeah, maybe you should yell and maybe the others should be a bit more quiet. Shh. Yes, exactly. We have two equations with two unknowns. Substitute V star from this equation. Equation 1, equation 2. So now it's easy. So we just substitute. So we have V star is equal to square root gamma RT star, or V star squared is gamma R T star. So we substitute that into this one. So we find CPT0 is CPT star plus a half gamma R T star is equal to, so T star times CP plus gamma R over 2. So T star, that was the one we were after, is equal to CPT0 divided by that one, CP plus gamma R over 2. Yeah? So now it's a bit boring. So what do we fill in? No? Ah. Problem solved. So CPT0, CP, 1008, given up there. T0, given up there 1200, dividing by CP, 1008, plus a half, gamma, 1.4, R over 2, and R So we find T star then with our R of 288 equal to 1000 Kelvin. So we started, look what compressible flows can do, right? Compressible flow, we started with a temperature in the reservoir 1200 Kelvin, we have 1000 Kelvin in the throat, and we have 310 Kelvin at the exit. Yeah, you spoke lots after the break, now we have to stay longer. Yeah. Question B. Sorry? Calculate the airspeed in the throat. So now the airspeed in the throat, we can use the relation we derived earlier. V is square root gamma RT. Because in the throat we have V is equal to A, so we can use that relation, right? And we just derived that the temperature in the throat is 1000. So we have a speed of 640 meters per second inside the throat. So what is the speed of sound in the throat? 640 meters per second. So some people have sort of in their head that the speed of sound is 340 meters per second. Yes, that's true at standard sea level conditions. So at that temperature, pressure and density we have 340 meters per second, but it can actually change. So inside the throat for compressible flows we have now a speed of sound of 640 meters per second. Now then number C is to calculate the Mach number in the test section, and number D is calculate the area of the throat in the cross section, and I will continue with that next lecture. See you.
Please visit our OpenCourseware website for more information. See you at our next podcast.